Hello. Hello, everyone. Let's start more one PD seminar. I hope that everyone is fine. Then today we have the pleasure to receive the Professor Tiarlos Cruz, the Universidade Federal de Alagoas, that will talk to us Scalar curvature, mean curvature, and static metrics.
So, first of all, I'd like to thank the invitation. This is a great pleasure to be here giving this seminar of differential geometry. uh, Today, I want to talk about the scalar curvature, mean curvature, and static metrics. And what? Mm, oh, okay, right. So this is my plan for today, and I'd like to talk about scalar curvature and static metric. To talk about the importance of this matrix, I'd like to present the definition, which are the static matrix of boundary, some properties and examples, and finally, I'd like to present a chain stack result and a uniqueness result. So, so let me start here with the scalar curvature. And we know that the scalar curvature is the weakest local invariant of a Riemannian manifold. And in dimension 2, the scalar curvature is just twice the Gaussian curvature. And this is so important because we have the Gauss-Bonnet theorem that says that the integral over the surface of the Gaussian curvature depends on the Euler characteristic. And then there's a link between the geometry and topology of the surface. When the dimension is greater than 2, we have, for instance, that the scalar curvature controls the volume of geodesic balls in an infinitesimal level. And as we can see here, and with this expansion here, right? But now I'd like to consider this map in the space of the Riemannian matrix. And we know that given a infinitesimal variation 8, well, now calculation shows that the variation of the scalar curvature is given by this expression here, which depends on the Laplacian of the metric, the trace, the divergence, and this ridge curvature. And then after integration by parts, we'll have the L2 adjoint is given by this expression here. We'll have the Hessian of V minus the Laplacian and the metric G. I'll have minus V, the ridge curvature. And so we say that a metric is static if this equation here is equal to 0, right? And so we have this, in other words, static if the kernel of that joint is non-trivial. And also, if we have a function satisfying this equation here, this function is called the static potential, right? And this kind of equation is important in general relativity because a solution of this equation here is equivalent to the assertion that this manifold here, this Lorentzian manifold, this product manifold with this metric is a solution of the Einstein field equation in the vacuum. And more, we know that this guy here is scaling, so the time slice or total geodesic is isometric to each other. And in other words, you're saying that this Lorentzian manifold describe a universe involving time so that nothing changes. In other words, static, right? Okay. Let me present some examples. And the first example is the sphere. Okay. So we have the sphere with this function here, the coordinate is an example of a static manifold with this function V. The flat torus if you consider the function v as a constant, we'll have to satisfy this equation here. This product manifold with this product metric here with the potential, which depends on which is given by the sign. And of course, we have the hyperbolic space is another example of manifold which is static. And this we have this example in particular, which is very interesting, which is the Schwarzschild. The Schwarzschild is a manifold as a manifold product manifold, such that we have this metric here, and m is a mass parameter, which is a positive number, and we have r, the radius of these spheres. So for this manifold, this function here is our potential. It's a potential function, and it depends on m and r. And here we have our level set, zero level set, which is a sphere, and this sphere is very important, for example, in the Penrose inequality, right? So, but we note that all of these maps have constant scalar curvature, and it's not a coincidence because we have these properties here. If we have this manifold, which emits the potential start potential V, then the scalar curvature is constant. And it's not so difficult because it's just to take the divergence of this expression and the trace. And so from computations, we can prove that the scalar curvature is in fact the constant. Also have the zero as a regular value of this function V, and more that this level set is totally geodesic. And the example is the sphere. So we have the sphere, here. We'll have our potential, which is the coordinates. We'll have this surface here, which is a totally geodesic sphere, sigma -1 at 0. This part is positive, this part is negative. And then we have this guy here is a surface, embedded surface, a very good surface. And also this with this property here, the norm of the gradients is locally constant. Locally constant means that it's constant in each connect components. And so we'll have a normal here, and this normal, it's but it's a minus the gradient over the norm of the gradient. Okay. And also have this metric is a critical point of this functional in the space of the matrix. It's just a computation, right? So a remark is that in general relativity, this level set here, it's called the event horizon, right? Okay, but there is another kind of definition, which is a manifold, which is a static manifold with boundary, which means that we consider here that the boundary is just this level set here. In other words, we have this, we consider just this part, and in fact, this is our boundary. And so this is NM and V equal to 0 on M, on the boundary of M. And so we have this manifold here, and the boundary in this case is -1 at 0. This is our sigma, right? So this is a type of boundary problem. And of course, we have a lot of examples. The first is the Schwarzschild, where we consider this positive part. This is our boundary. The second example is the hemisphere. Is here. Okay, this is a very simple example. The another example is the radii, which is a cylinder of the sphere, where the metric is this product metric here, and our potential function depends on the sign. Okay. the matrix is G, is this metric here, this product metric.
Yeah, but
Yeah. So we have the, yeah, yeah, exactly.
I believe that the problem above is linear.
Linear in B. Which problem? This year? Ah, we have the Herschel here. So just I think we have the manifold, a metric, a potential function. I consider these three objects here, these three things. So the another example is the Schwarzschild de Sitter, which is with a metric in this product manifold, where this I is a suitable interval, which in fact is a interval such that this will have the solution of this equation here, and our metric depends on this R. It depends on this function V, which is our potential, static potential. And so the Schwarzschild de Sitter is a family of manifold between the hemisphere and the radii, right? Radii. It's this here. And here we have this family, which are manifold, which has two boundary components. One of them is unstable, and here is strictly stable. Stable in the sense of minimal surface of the second variation of the area, right? Okay. And finally, we have the ball, which is not an example manifold with static manifold, which is very sad because the ball is a nice example of manifold with boundary, and this definition here does not capture this example in particular. So the ball is not an example. Where? In which part? Yeah,
escape by a constant. So first two terms are filled, and then the other one will give you a constant and reach into the other side. Probably.
but I believe that if you modify the problem, maybe this is possible because there's a V-stock method, which is method where instead of the scalar curvature, we consider the volume, and then using the volume, the scalar curvature in the volume, maybe here could be a constant. There's something in this direction. For instance, if in the V-stock metric, which were some metrics defined by Miao-Tan, they consider some spherical caps, and maybe here this function, this part is constant, this potential. I'm not sure. Okay, so why is important to study this kind of metric? This is important, for example, because the prescribed curvature problem in a series of work of Carlos and Warren in 1974, 1975. But what means this problem? And the prescribed curvature problem says the following: given a manifold and a function, a smooth function, the prescribed curvature problem consists in finding a Riemannian metric such that the scalar curvature is exactly equal to this function f. And so in 1974, 75, Carlos and Warren proved that if you have a manifold with dimension greater than or equal to 3 and closed connected, we have three possibility of kind of manifolds. We have the manifold type 1, type 2, or type 3. The manifold type 1, for this manifold, we have that this problem here is solvable for any smooth function. Type 2, this problem is solvable if only if this function is negative somewhere, or this function as identically equal to 0. And type 3, if this problem here is solvable, if only if this x is negative somewhere. And this is in dimension greater than 2. In dimension 2, have the Euler characteristic. And this is special because the Euler characteristic gives necessary a sufficient condition to solve this kind of problem. Also very strong. And the idea is because they solve this problem for matrix in a non-static matrix, right? So, but this problem is also important in the problem deforming the scalar curvature by Bourguignon, Fischer-Matz, and Corvino. For example, a consequence of the Bourguignon's result is that the set of non-static matrix is an open dense set in the space of matrix. And after that, Fischer and Matz proved some local surjectivity of the scalar curvature map under some assumptions. And the assumption is the metric is scalar flat, but the root tensor is not identically equal to 0. And more, this quotient here, it's not a constant in the spectrum of the Laplacian, right? So this is the condition. Moreover, okay. And however, the Corvinus contribution was to localize this deformation in a certain compact domain. For example, they proved that if you have a non-static manifold, it is possible to find a small compact such that it is possible to decrease the scalar curvature. Okay. And also this problem is important in general relativity, and with this work of the Corvino, Ambrosio, Shen, Butin, Masudio, Borghini, Crucial, Mazzieri, and many others. This problem is also, we have some rigidity classification results, especially in dimension 3 by Kobayashi, Lafontaine, Agostini, Mazzieri, Ambrosio, and etc., etc., etc. So this problem is very important in some sense in a particular area. But here, I'd like to present here a new definition of static manifolds, which are the static manifold with boundary. What this? So here, I'd like to consider the boundary, and for this, I'd like to consider. I like to include the mean curvature of the boundary. In fact, twice the mean curvature, and then we consider this operator here in the space of the Riemannian matrix, and for this operator, we consider the linearization, and having at hand this linearization after a direct calculation using the Green formula, we obtain that the L2 adjoint of this linearization is given by this expression, and this expression has another boundary operator. And for this boundary, and here we have this normal derivative, where this normal nu is the outward unit normal vector field to the boundary. And here, this guy here is the second fundamental form of the boundary with respect to this normal, right? And so let me right here have this normal derivative. This is the second fundamental form. Sorry, this is a tensor 0 on the boundary. Okay, and here we say that a manifold is static with boundary if satisfies this equation here, right? And also a function satisfying this equation, the identity here, it's called of static potential.
You explained this before, but why are you considering now both the scalar and mean curvature at the same time?
No, at the same time. At the same time. Okay, so examples. The hemisphere is an example. Hemisphere in the Euclidean space is an example of method for satisfying this equation here. The half short shield. The half short shield is the short shield where here we cut the short shield in the vertical direction, and here we have a manifold such that this is a boundary, which is a non-compact boundary, which is totally geodesic. And here we have our level set here, zero level set, which is in this case here is the free boundary mean surface. And we have the so this is the half first shield. This definition was this name was given by Lima Almaraz Barbosa, and this one half first shield was given by this name. Half first shield was given by Eichmer and Koerber, Thomas Koerber, right? Another example is the torus. So if you consider the flat torus with this flat matrix, then this product here with this product matrix is an example of static manifold with boundary. And in fact, it's a flat manifold with total geodesic boundary, so it's not so difficult to conclude that this satisfies the equation here. And here we obtain the ball. And the ball is a base example of compact static manifold of boundary in the Euclidean, it's the Euclidean closed unit ball. And here our potential is this function here, which is the inner product of x and v, where x belongs to the ball and v is a non-trivial vector in the Euclidean space. And in this case, our level set is a disk, which is a total geodesic disk, this guy here, okay? The disk which contains the origin. And the second important example for us is a special piece of the Schwarzschild. And so if we consider M mass parameter, positive mass parameter, and three-dimensional Schwarzschild, we'll have our potential function V, which is defined by M and R. And we know that in the Schwarzschild, the Schwarzschild is foliated by spheres, by total umbilical spheres, such that the mean curvature depends explicitly of the static potential V. And so the normal derivative with this normal unity normal vector here, it's equal to an expression which depends on M and R. And in order to satisfy this equation here, we'll have to assume that R is equal to 3M. In other words, our example is a compact example such that the boundary or the boundary is a sphere with this radius, specific radius here. And in this example here, it's different because here our zero level set is in the interior, right? And this problem was, and this not this problem, but this example here was very impressive for us because this specifically this sphere here is related to the notion of photon sphere, right? And which is very important in general relativity. So this was very impressive. And here are some properties, general properties. And the first property is, so we have our zero level set, sigma, and we know that this is an embedded totally geodesic hypersurface in M, but here we have two possibilities. Sigma intersect or does not intersect the boundary of M. If sigma does not intersect the boundary, then sigma is a total geodesic hypersurface in the interior, right? But if sigma intersects the boundary of M, then each connected component is a free boundary totally geodesic hypersurface. And recall that a surface is free boundary set to be free boundary if the boundary meets the boundary of M orthogonally, right? So here we have many examples of free boundary remote surface in the ball. And this is very interesting because this is the link between minimal surface and the manifolds. So we have this as before, have this number here, which is the norm of the gradient V, is a positive constant on each connected component, and as in the closed case, because this calculation is in the interior, we'll have the scalar curvature is a constant, but here we have a new information. The boundary is totally umbilical, and the mean curvature is constant on each connected component of the boundary. So this is new. So, I'd like to present some results in the literature about this new kind of metric. And first, this metric, this new kind of metric is important, for example, in a prescribed curvature problem, where you consider at the same time the scalar curvature and the mean curvature. This is very important in the problem of deforming the scalar curvature and the mean curvature. For example, for instance, this work here, it's a new work, a very recent work. This guy here is a change student, was a change student, I guess, and he proved a version of the Corvinus work. In other words, he localized the formation of the scalar curvature, mean curvature in some small compact domains. Also, this problem was important in general relativity with this work here of Lim and Almaraz, and they proved some rigidity in non-compact static domain, the hyperbolic space via positive math theorem. But unfortunately, we have just few results about classification and rigidity of static manifold with boundary. And so I'd like to present one. Before, let me go back to the closed case, right? And using a technique developed by Robinson to show the uniqueness of the Schwarzschild black hole, Shan give a sharp upper bound for this for the area of this level set, and we have this theorem here that says that okay, I have a three-dimensional static manifold which is compact with boundary, sorry, where it's compact, and our sigma is connected, and the scalar curvature connected, and the scalar curvature is equal to 6. 6 here is just a normalization because the scalar curvature is a constant. Then we have that our level set has to be a 3 sphere and more. The area is less than 4 pi, less than or equal to 4 pi. And moreover, the quality holds if only if our manifold is isometric to the standard sphere. So, we have our first result, which is an Argov chance theorem, but in our setting. And then we proved that assume that we have a three-dimensional manifold, right? And which is compact, oriented as a compact static manifold with boundary. The metric is a scalar flat, but the mean curvature of the boundary is equal to 2. And our potential, our zero level set is connected. Then we have two possibilities. A, if sigma intersect the boundary, we have that sigma is a free boundary totally geodesic to disks, and more, the area is less than or equal to pi. And if the equality holds, our manifolds isometric the Euclidean ball. But we have the second case, and the second case says that if sigma does not intersect the boundary, then sigma is a total geodesic sphere, and the area is pi. And let me say that so here we have no rigidity result, but here we don't have one. But we can see in this example here that the case 2 can occur, in fact, because if you consider our example whose boundary is the photon sphere, if we normalize the mapping in order to the mean curvature to be equal to this constant, then the area of this level set it's less to pi. So the example can occur. So let me give the idea of the proof of our results. So in order to prove our results, we have to apply this Pohozaev type integral identity due to chance, which in fact is integration by parts, where this here is the lead derivative of the metric, and this tensor here is trace free part of the rich tensor. Okay, so let me divide into cases. The case 1, if sigma does not intersect the boundary. If sigma does not intersect the boundary, we know by the properties that this sigma is a closed total geodetic surface in the interior. Okay. Then consider this omega here. This omega is a domain such that S and sigma bounded by S and sigma. Okay. Omega is the part where this V is positive. And so we use the Pohozaev type integral in the quality identity in just in this part here. And so if our x is equal to the gradient of V, we have that this integral here over omega depends on this integral over sigma and S. First, the norm of the gradient is a constant, so we know this. And this rich curvature, we can change this rich curvature here by minus the Gaussian curvature, and this is because the Gauss equation. And this is very good because we have the Gauss-Bonnet theorem. For the second part here, we have this. We know that V reach nu is equal to this relation here because the static equation in the second equality here is because the Laplacian of the immersion, the Laplacian comparison, and so we obtain that this, in fact, this integral over omega, which is non-negative because V is positive, it's equal to this constant. So we'll have that this. So we have the area is less than or equal to pi Euler characteristic. So we see here that the Euler characteristic has to be positive, and then our sigma has to be a sphere. And if our sigma is a sphere, and the area is less than or equal to pi, right? But unfortunately, we don't have the equality, because if you have the equality here, then we have equality in this expression. And if we have this equality here, we'll have that our manifold is H flat, but since we are in dimension 3, our manifold is flat, and using Gauss equation, our sigma would be flat, which is a contradiction because our sigma is a sphere. So we don't have the equality here. So it remains to analyze the second case. What happens if sigma intersects the boundary? But in this case, we know, but by that property, that sigma is a free boundary total geodetic surface. And now we consider the omega I is the set where V is positive, and here we have two boundary components. We have this boundary component here, sigma, and this here, which is S. And here we have two normal, the normal of S and the normal of sigma. Then, as before, we have the integral of V. This integral, which is non-negative, is equal to this number here, this constant. But now, since the Euler characteristic, since the manifold, the surface has a boundary, if in the Euler characteristic is positive, our sigma has to be this. And so the oil characteristic is equal to and then the area is less than or equal to pi. And so and for the quality, if the area of sigma is equal to pi, then as before, our manifold is H flat, which implies that the manifold is flat. This in the interior. With respect to the boundary, we know that the boundaries connect, is umbilical, and has constant Gauss curvature equal to 1. This part here, we use the Gauss equation. And so we have the boundary is isometric sphere. And then we have a manifold with boundary, which is flat in the interior, and the boundary is a sphere, so we have the both. But here, in this example, we see that we have some rigidity result here. So it's very natural to ask what happens in this case here if there's some kind of rigidity here. And so we know there's an example here, an example such that sigma is in the interior, and the sigma is in the interior, and the scalar curvature is equal to 0, the mean curvature is equal to 2. Then a natural ask about this uniqueness, and then in our next result, we obtain some progress in this topic. And so we prove this result here. So suppose that we have a manifold, a three-dimensional manifold, which is a static manifold boundary, and such that the metric is a scalar flat. The mean curvature of the boundary is positive. Our sigma is connected is in the interior, and omega is a connect component of m minus sigma. Then 1. That there is only one component of the boundary of omega with positive mean curvature, and 2. If S denotes the component of the boundary of positive mean curvature, then S is a sphere, and we have an inequality here involving the mean curvature and S, the area of S. And moreover, if the equality holds, our domain is isometric, so that special piece of the short shield, the piece of the short shield such that the boundary is a photon sphere. And so for the area estimates, it's a very simple because we have this general inequality here, right? We have the general inequality here, and for in this part here, we use this formula that involves the Laplacian of M and the Laplacian of S, and using this identity here, we use the static equation, and using the Gauss equation, then we obtain this identity here, and then the result follows by using integration by parts in Gauss-Bonnet theorem. So so here I have an important remark. When we have the equality here, it is possible to prove with this computation here that the equality holds if only if this function v is constant on S, right? And if the scalar curvature is equal to 0, then either this S is a totally geodesic to Tor, or it is a totally umbilical to sphere. In our case, since the mean curvature is positive, then this S is in fact a totally umbilical to sphere, right? So this is the proof of the area estimate. And then I'd like to prove that we have just one component with positive mean curvature. So in this case, we have our sigma here, and we have possibly many boundary components here of S. So we have some xi. Si. Okay, so this is our omega. So we have that because the previous remark, we know that the mean curvature is SY. Since we know that the mean curvature of each SY is positive, we have that each of them are totally umbilical two spheres, right? Then our line is our S connected, so we have just one boundary component in this part, and in other words, k is equal to 1. And the idea is we have a three-dimensional manifold which is scalar flat, so it is possible to construct a four-dimensional manifold such that we have a matrix that look like this, and this matrix is H flat, and the boundary has strictly mean convex, strictly a positive mean curvature, right? Now that's strictly mean convex boundary. And in fact, this N4 is a quotient space given by this expression, or where we have a special equivalence relation. In other words, we can imagine this N4 as a manifold obtained by rotate M around S, right? And so, since we have a matrix such that is H flat and whose boundaries strictly mean convex, by a standard argument involving minimizing geodesics, this boundaries connects. If the boundary of N is connect, the boundary of our S's connect as well. And this is true because if we have more than one boundary component, there's a minimizing, it is possible to construct a minimizing connecting one, the both. But because this condition here, this geodesic has to be unstable. So this is a contradiction. Okay. And for the rigidity, we consider we have some argument here for the rigidity. So assume that we have the quality for that inequality. Assume that we have the quality in that part. Then we have omega, such that these are our sigma. Okay, let me. So we have our sigma, this our omega, and we have here a two sphere, which is totally umbilical, and we consider here a Schwarzschild starting from the sphere of radius 3m. Okay, so this part here is the Schwarzschild. Then, since we have the quality, and that we have the quality. Since we have the quality there, the potential function is constant here, and it's supposed to prove that this surface here are isometric. And then we glue this surface, and then we obtain a manifold that look like this. Where here it's, let me call m tilde plus with some metric here, such that this metric here it's smooth away from this gluing surface, and C11 here. So the next step is to reflect this manifold here, and then we'll have this m tilde minus, and we'll have this metric here, and so we obtain a manifold m tilde g tilde, where this manifold here is composed by m plus tilde and m minus tilde. All right. So the next step is to consider an m hat, which is a manifold with a conformally. It's a manifold with this conformal metric, where g hat it's u4 g tilde, where this metric here is a metric such that this end here, this part here, sorry, this part here has ADM mass equal to 0, and for this end, it would compactify like this. And then we'll obtain a closed manifold, and the next step is to apply the positive mass theorem, or in fact, a weak version of this positive mass theorem proved by Bartnik. And then for this math, using this result, we prove that in fact this manifold has to be a plane. And so if this manifold is a plane, this manifold here is conformally flat. And if this manifold is conformally flat, is the Schwarzschild. And if this manifold is the Schwarzschild, this is the Schwarzschild. So this is the result. Okay, so this is the idea of the proof of this result. And so this is the idea. Some question?
Thank you for your talk. I would like to ask you, how do you choose U again? You said that you close it.
Yes.
But is there any natural way to define such a U? I mean, how do you come up with it?
Yeah, I'll have to. It's a lot of work.
Then another question, if you go back to the very definition of this new concept of the metric and the V coupled in a way, you gave the first definition was a function of the called psi G, and then you took the first the linear axis, and then you took the adjoint.
Ultra joint.
Yeah, and then my question: how do you come up with such a psi or the original function? Does this come from a variational point of view, or like, because obviously the adjoint operator is exactly the one that you define in the equation, but other than that, how one come up with such an object?
Yeah, because in fact we have our map, right? And then with this map we can. So let me consider this linearization, and the next steps consider adjoint. So the idea is to consider this composition. Use this composition as supposed to prove, for example, that this map uses local surjective, because this problem here, it's elliptic in some sense. So the idea is here in this composition. So I have a list of problems, but let me. Okay, I'll stop here.
Thank you, Tiarlos, for the presentation. Someone has any question or comment?
So does this problem with the boundary have also some sort of interpretation, general relativity, or is it just the problem?
No, there's a motivation, because the boundary, sorry, and the closed case will have because that field scaling is supposed to prove that manifold it's will have it's foliated by isometric surface, and in fact this Lorentzian manifold here it's Einstein satisfies the Einstein equation. When you consider the boundary, we'll have something similar, but here our manifold satisfies the Einstein equation, but the boundary is umbilical. There is also another motivation using general relativity as well.
Well, usually when you consider general relativity, you can continue your manifold coming to the other side, and inside the black hole, inside passing the NMR, right? Can you do something like that?
Yeah. all of these problems in general relativity without boundary has a motivation with boundary, which is more interesting for physical guys. But yes, we have a lot of motivation in general relativity.
So you do that assuming that the scalar curvature is 0 and the mean curvature is 2.
Mhm.
So we do the result.
Mhm.
So does it make sense to ask if you put, I don't know, the opposite? Mean curvature to be 0 and the scalar curvature to be something. Do you have any rigidity stuff? Or just, it doesn't make any sense?
Yeah, this makes sense because we have this model here. Probably this is the rigidity for the. It is supposed to prove that the model is a half short shield, which is now scalar curvature equal to positive constant. No, I don't know. But if you consider negative constant, probably you can do that. You can do something similar to the anti-de Sitter short shield, because the anti-de Sitter short shield has a scalar curvature equal to -6, and we have two kinds of problems. It is possible to consider the Sitter short shield with such that the horizon has positive curvature, or such that the horizon is minimal. In the case, it is possible to consider the case where the horizon has a minimal boundary. And yeah, maybe you can consider a problem like this. Okay, maybe. The problem, in fact, is the positive mass theorem. I don't know if there's a weak version of the positive mass theorem, the hyperbolic space.
A very naive question, but are all static Einstein manifolds static in your definition, or are all solutions of the Einstein equation which have active?
And yeah, I'm talking about the Lorentzian manifold. Yeah, all of them are static, or sorry, or Einstein. Yeah, yeah, all of them are Einstein. In the vacuum, probably you can consider some problem using charge or something like that, but yeah.
Another question? It's right behind that slide, but is there any higher dimension of rigidity phenomenon?
Which result? The first one?
Either PDE at all.
Okay. For the first result, let me go back here for our first result. In this first result here, maybe the problem is the Gauss theorem, right? But I believe that we have some result, some versions of the Shen's result in the high dimensional case, and probably you can, I don't know, you can try to prove something similar, but I don't know. But for the second case and for the second case here, maybe yes. But as I said before, the problem is to obtain this inequality here, because also the Gauss theorem. But they are a good question. Very good question. Ricardo. Okay.
Any question from the people online? No? Then let's say thanks again, Professor.